Hey folks, welcome to Advent of Code in F Sharp, day 14 already. Wow. I see that we have 2 minutes to spare, so I wanted to show something. This weekend I mentioned that, hey, day 11 looks cool, maybe we should write a quick visualization for that. And yesterday I had some free time, so I wrote a quick visualization for that. Trigger warning, this might get a bit flashy. And I decided to use something I have never used before, which is Fable transpiler that transpiles F# code to JavaScript, and then the Elmish library, that's a small library that allows you to write Elm architecture apps, so model view update kind of things, using F#. And yeah, that was a really cool experiment. Maybe I'm gonna give a quick demo of what I'm talking about. If you haven't seen Elm or Elm architecture already, it's really interesting. So every web app you write in Elm or Elmish has 3 parts: model, view, and update. The model is just your data. So here we have a model with just the timestamp, the current generation, and the grid of flashing octopods or octopus. So that's one part, model. Second part is a function called update. And that function takes a command, or no, it takes a message. This is like an event that happens in your UI. So for example, someone clicked this button, or a timer you fire every second has fired. So this is the first argument, and the second argument is the current model, so the current state of your web app. And in this update function, you typically just like pattern match on the event that's coming in and do something depending on which event it is. I only have one event in my app, which is a tick I fire every 100 milliseconds, something like that. And every tick we just advance the grid by 1. So that's the second part, update function. And the third part of an Elm app or an Elmish app is a view function, which takes a model, so the current version of the state, and it returns a React element, so the HTML basically, or something that will end up being the HTML. This looks really weird if you're used to seeing HTML, but this is basically describing my UI in a declarative state, and I have my model, so I can fill my template or my HTML with whatever I want from the model. And if you look down here, this is how you wire everything together. You just say build a program with this initial model, this update function, this view function, and go have fun. So writing this app took not that much time. Getting a Hello World Elmish Fable app up and running, that was something else. Which is why I didn't live stream that part. But now that we have a first version, or we have one of the days, we have an Elm app for that, or an Elmish app for that, maybe we can do a bit more visualizations if we have interesting problems to take a look at. I don't know if I dropped to my banner, so I'm going to keep my banner page on here for just a second while I get ready for day 14. Okay, so let's drop to day 14. What do we have? I hope it's going to be a quick and easy one. I have to be in the office in 2 hours, so please let this be a quick one, or we'll have to cut the stream short. Day 14, extended polymerization. Oh no, this is giving me nightmares. We had a puzzle that looked like this a couple of years ago. Did not like that one. But anyway, incredible pressures at this depth are starting to put a strain on your submarine. The sub has polymerization equipment that would produce suitable materials to reinforce the submarine, and the nearby volcanically active caves should even have the necessary input elements in sufficient quantities. Submarine manual contains instructions for finding the optimal polymer formula. Specifically, it offers a polymer template and a list of pair insertion rules. Phew. Which is our input. You just need to work out what polymer would result after repeating the pair insertion process a few times. Yeah, this is a grammar. Here we go. Is it? First line is the polymer template. This is the starting point of the process. Yeah, so it's a substitution kind of grammar thing. The following section defines pair insertion rules. A rule like A, B transforms to C. Yeah, we're just going to reduce a string given a grammar. Means that when elements A and B are immediately adjacent, element C, oh no, we're growing it, should be inserted between them. Okay, so our polymer increases. So starting with N and C, B, the first step simultaneously considers all three pairs. So yeah, we take a look at all pairs. If you have a match, we have to insert something that it matches on the right hand side. Yeah. Whoa, this is... Okay, so we look at every pair. If we have a match, we insert. Note that these pairs overlap. Yes. Also, because all pairs are considered simultaneously, inserted elements are not considered to be part of a pair until the next step. Yeah. After the first step of this process, the polymer becomes something with 3 insertions. Yeah, here are the results of a few steps using the rules. Okay, cool. Polymer grows quickly. I don't like hearing that. After 5 steps, it's already at 97. After 10 steps, it's 3000. This is pretty exponential. So how many steps? 10 steps for part 1. I think we can hammer out a 10-step part 1 in an hour. What do we need to look? Do we need to do the naive thing? That's question 1. What are we doing? So after step 10, it has a length of 3000. And then we count how many times the different characters occur. Taking the quantity of the most common element and subtracting the quantity of the least common element. This produces a number, which is the number we're looking for. Apply 10 steps of insertion to the polymer template and find the most and least common elements. What do you get if you take the quantity of the most common element? Yeah, okay. We get where this is going. It's a big grammar. Let's get rid of our Elmish. So we have a template on the first line, then we have a new line, and then we have a whole set of rules. Let's also grab the example. For the pair thing, can we use pairwise? Let's quickly verify that. So if we have a list and we do pairwise, is this what we're looking for? 1, 2, 2, 3, 3, 4. Yeah, so pairwise will work wonders for today. So we need to parse. Let's parse. What is the data structure for this thing? Just a lookup table? Yeah, let's build a lookup table mapping the tuple or the pair on the left to an element on the right. Okay, so parsing. Let's split on... Nope, actually no, it's an array. Let's just take while... Nope, we know the first line. I'm getting there, I'm getting there. So this is the template. Will we work with raw strings? Yes, we will. Just, I'm gonna convert to a list that works a bit nicer. So I'm just gonna use a list of characters. Sorry, why is this empty? It's not empty, okay. Yeah, that's the template. Now let's parse the, what do we call those things? Pair insertion rules. I'm just gonna call them rules. Let's skip the first 2. So we're dropped down to the first line. Yep. And then just map over some kind of parse rule function. Oh, my fingers are not awake yet. So what do? We just split on... This here, we've been working with just like string.split, and it's been doing wonders. It's been working wonders. So let's... do you want to call it from to? I don't know. Does this work? Let's take a look, see. So source, destination. I'm just gonna use tuples. It'll make our life a bit easier. No, it won't make our life a bit easier. It will make our life easier if we split source into its components or into its characters. I think so. Sequence, list of sequences the other way around. I want to do it. So I want to have a sequence of characters, not a string. That is better. And I think if we now just do a windowed or a pairwise, we can loop over everything and start replacing. So yeah, I think this is our parse down. So I'm going to wrap this into a function. And let's return both. So template and the rules. Let's see if we can parse our example. What is the problem here? Character is not compatible with type sequence A. Input is not a string, it's a string array. There we go. This appears to do something. Does it appear correct? Yeah, I think so. Cool. We have parsed. Now we need to apply the insertion. What was it called again? First step of what? What is the first step of what? What are we doing again? Repeating a pair insertion process. I'm just gonna write a function process. So what will this function do? It will process a single step of the pair insertion thing. So we need to know the current template or the current string we're building. I don't think it's called template anymore once we're looping, and the rules, and we give a new template. Process is a reserved keyword. Let's not go there. I'm gonna call it process 1. Sure. One step of the pair insertion algorithm. Okay. What do we need to do? No idea. I'm not gonna dump it into a function just yet if we don't know what to do. So template. In that case, I'm gonna do it here. So template. What is templated again? Array or list? A list. So if we take everything in that list pairwise, we have NN and CCB. That looks correct. And then we just look up every one of those in the rules. And now I see this and I think maybe it makes sense to put those in a lookup table. So let's do exactly that. So now this is an array. Sorry, a map instead of an array. Yeah, so we can look up stuff a bit faster. And for every pair, we just need to do the lookup. If there is something, we insert something. If there is nothing, we leave it as is. Sounds like a plan. So for every pair, we map and we do a apply rules to this pair. So let's write a apply function. Apply rules to a pair. A pair is always two things. Now let's do that later. So we can do a lookup. We can do a lookup. We can do a lookup. So we can do a lookup in the map of rules. I don't think there is going to be one always. So let's do a try find instead of a find. We need to try to find a value for pair. I'm not gonna do fancy stuff here. Let's just pattern match on this. So try to look up something. Nothing. Cool. We do nothing. Found something. Well, let's destructure the pair a bit more. And let's return A, B, and whatever is in between. And the in-between thing is whatever we found in our map. So that is some result, some right-hand side of a production rule. A is a single element, so let's use this thing. That looks weird. I'm gonna drop back to the non-performant list append. There we go. We might have a performance issue today. And we have a compiler problem. Type mismatch, expecting a tuple of characters, but given list. Oh, what? That's a character list. We do this pairwise. And for every pair, we want to do something. So it's not making sense to me, this compiler. Okay. What is it saying? Given a car list string and it... Okay. It's confusing because I expect some things to be a string and some things to be a list of characters, and those are not very compatible. Where do I make the assumption that one is a string, and where do I make the assumption that the other is a list of characters? I don't see a string anywhere. So let's add some explicit types. Chat, if you see what's happening, or where I do something string-like, let me know. What is the type of our lookup table? Right-hand side, or the values in our map are strings. That was a whoopsie on my part. Parse rule. Oh yeah, we do this thing. That's also made at a list. On the right-hand side. Okay, these are pairs, they're not lists. That's even easier then. I hope we don't have to do more than a pairwise. That might hurt a bit for today. Okay, we're getting somewhere. A is a character, B is a character, result is a list of characters. Yes. So what is not going? It should return a list of characters, right? Oh yeah, okay, this is the problem. So this is correct, but if we don't have to do anything, I just want to return a list of characters. Why did I do this as a pair? Yeah, that's a good question. Let's drop back out of that change. So this is a list of characters, not a pair. So I'm gonna transform that list of characters, or that pair, into a list of characters. There we go. This is totally unreadable to me already, so there you go. One variable or one letter variable names are sometimes a good idea, but they get out of hand really quickly. I think this might be... Oh no. Now we just did 3 insertions, but we have to smoosh these things back together, right? Can we drop? No. I was thinking, can we drop like the last character? How do we smoosh these things back together? Or should we not do the string inserts over there? How do we smooch these back together? We know stuff. We know stuff. We know that the last thing in here is always the first thing in here. We know that the last thing in here is always the first thing in here. How do we unpairwise? We could get rid of the last element in every of these sublists, except for the last one. There we need to do a bit of a hack and insert that one back in again, or just not touch the last element. Don't like what I'm saying, but yeah, I think that's going to be the fastest, or at least my brain can come up with nothing better. So let's call this, it's a terrible name, but these are like the sub step we just did, the pairs where we inserted something if we had to insert something. Now let's smoosh those back together by what? By getting rid of the last element. Yeah, let's try that as a first step. So we're doing too much work. That's never a good sign. I think part 2 performance-wise might hurt us, but we'll see. We'll get there when we get here. What do we need to do here? How do you remove the last element of a list? Returns a new list with the item at the given index removed. Yeah, but we don't really know how long this list is. It can be 2 or 3. That's not a problem. So remove the... Wait, it's -1, right? Oh. No, stop what I'm doing. So let's try this out. So we do a sublist, the length of that, and we remove from sublist this element. Yes. So this will be correct for everything except... This will not be correct. -1, sorry. This will be correct for everything except the last one. Do I need more parentheses around this thing? I don't even know what I'm doing anymore. Okay. There we go. Does this compile? Yes, it does. Does that look correct? I think it might. Except for that B. Except for that B. I'm not even gonna worry about that. I'm just gonna do... I'm just gonna do a very dirty thing and grab that thing. Now we have everything. So we can just smoosh that list together into a single list with a flat map, or what we call a list.collect. And if we append last character on that, yeah, I think we might actually be done. It's not the cleanest code I've written by far, and performance-wise we might have a problem, as I said, but let's worry about that in a couple of minutes. Does this look correct? Do we have NCN BCHB? NCN BCHB, that looks correct. So this is a single step. So this is process 1. The template, let's use T. Where do we use the rules? Over here. And this is recombining. Yeah, I think that's it. And that's our beautiful process 1. And that should all still work. Yes. How many times did we need to do it? 10 steps. I'm just gonna do an after 10 and do a, what was it? Process 1. Given our template and the rules. Can I switch those? I can switch those. I should switch those. Because now I can pipe. So we can just do template, pipe, process 1. No? Yeah, it doesn't know rules, it knows R. So this is 1 step, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the way you do it, ladies and gentlemen. Everyone. No? I thought we were done. Okay, this looks better. Quick sanity check. How many characters do we have? 3073. That, yeah, it's correct. Now, what do we need to do? Count by, or count how many the different characters. Yeah, that's what we need to do. What does count by do again? Applies a key generating function to each element. Can we do this? Count by ID. Is this what we are looking for? 1749. Yeah, that's exactly what we're looking for. And then we need the most common element and the least common element. So it's sort descending, for example. And no. We need to sort by the count, so that's the second element in a tuple. Otherwise we would be sorting on the tuples and it'll do an alphabetical comparison, I think, between the characters. That's not what we want. This is better. Okay. So these are the sorted counts. And we need sorted counts. No. Sorted counts. Sorted counts is a list. Oh, it's a sequence. Let's make that a list again. Is that actually a list? Yeah. Let's not make that a sequence again. Let's stay in the list world instead. Yeah, so this is the minimum. And we have a maximum. So I see C, no, I see B and H. 161 and 1749. And now we just subtract max minus minimum. And that gives us a magical number. Oh, we need to destructure. So we have the count, not the character. And that is 1588. I am removing code. 1588, yeah. So let's try to parse our input. Does it work without crashing? It does. Does this burn up our CPU already? Nope, that's cool. So we have a value around 3000. And it's correct. Cool, 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 cool. I am dreading what comes next. So let's just copy paste my file into a part 2. And if Visual Studio wants me, okay, we can continue. That was fun, that was cool, but now I see large numbers. Here we go. This needs some copy. Okay, part 2. The resulting polymer is not nearly strong enough to reinforce the submarine. You'll need to run more steps of the insertion process. Maybe 40 steps should do it. In the above example, most... Oh, these become large numbers. Is this crossing over integer range? It just might. That's interesting. That's really interesting. Okay, so the only thing that changes is the search size, or we need to do 40 of these insertion rules instead of 10. And then those counts become really, really, really big, which might be a problem. How many characters do we have? 1, 2, 3, 4, and they range in the 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah, in the billion, gazillions, in the gazillions. So yeah, we need probably to figure out a faster way to fix this. Have we seen something we can exploit? It's a long list of substitution things. I don't think there is a system in there. Is there? I don't see it. Will we try the stupid thing? Or no, it's not a stupid thing, it's a naive thing, and it would work if we had infinite computation capacity. Yes, we will try it. I am a sucker for running against brick walls. So, I'm gonna... I've noticed that several F# experts watch my YouTube videos. If you know a way of repeating a function like over a set, like some sort of fixed point, if there is a built-in function, I would like to know. I always write it myself. Which is cool, but if it exists, I would like to know. No, I'm gonna keep it over there. So I'm just gonna repeat the process n times. If n hits 0, we are done. And we can return the template. Otherwise, we repeat and decrease, and we apply process 1 of the template. And it has to be recursive. It's not too bad to hammer out, but... Oh, we also need rules, of course. And let's just provide them as an argument. We need to pass it into the recursive call. There we go. Is this correct, or am I off by 1? So after 10, nope, let's do the entire thing. Dropping everything in a function. Also the parsing. There we go. Now let's see if we can replace this with that repeat function. So if we solve the example, we get 1588. If we do this, but do a repeat 10 rules template, there we go. Do we still get 1588? It appears so. Let's validate our input. Almost 3000. Yeah, that was correct. So this is a 10 repeat. Now let's see how badly our CPU burns. I'm gonna also do some prints. So if n modulo 10. Oh no, it's only 40. We can just print out the current number we are repeating on. Okay, so this should be a bit more intensive. It's not even printing. It's going off doing its thing. Why is it not printing? Why am I not seeing prints? Because it's not flushing to console? How did I fix that in the past? Let's kill our console and do a print F. I remember this working and the print event not working. I cannot explain it. I am not an expert on low-level details. But does this print? No, this does not print. That's too bad. So we need to do something smarter. What is the smarter? What is the sucky part we're doing? We are doing a lot of not optimal parts. Like list appending, that's not cool. Remove at, that's also a linear search or a linear traversal. But maybe we need to look at the bigger picture. Not just micro optimizations, but a whole algorithm rethink. I said without having a clue on where we want to go, of course. If it ranges in the billions, that's crazy. That is actually crazy. Do they want us to calculate the actual 40th step? Oh, but you know what we could do? We could print out the counts for every number and see if we spot a pattern. Maybe there's like maybe our grammar is some kind of program and it contains some kind of loop, and maybe we can reverse engineer the loop. But that would mean we have to print out our counts, which is something I'm having trouble with, but this sounds like a plan to pursue, so let's give it a try. So actually, yeah, let's go back to 10. We know 10 works. Let's verify that 10 works. Works. Let's see if we can print something for 10 now. Oh, I am printing stuff. Why is this not showing in my... Okay, there it is. Beautiful. But instead of printing... What was that /D? I don't even know what I was trying to do there. New line, probably. Yeah, okay, so this gives us a print in between. Now let's do this thing. Let's count and let's print those out. So over here, let's do the exact same thing. So the template, let's count the characters and let's sort on character. And let's print those out. Let's maybe also grab... No, we need to count as well. So it's the character and the count. And let's just print out C character. We will find out soon. And D is digit. So character count. Yeah, I think this will give us enough information to see whether or not this is worth pursuing. Whoa. Visual Studio, don't give up on me. We are on a tight deadline today. Yeah, that's cool. But instead of doing this, let's do this. And let's print a new line here. I want to see all these things on one line for every generation. Oh, that's actually a lot bigger than I expected. That's a lot bigger than I expected. The example is only 3, 4. I did not take into account that our input. Oh, come on, I just want this to line up nicely. So we can start taking a look at Patterns. I'm giving up. No, I'm gonna put 2 more tabs in here. Beautiful. Beautiful, beautiful. Do we see something? I don't see anything because of this misalignment. Do we see something for V? +5, +3, plus... No, no, no. For S? Yeah, you know what? Sort by first, please. Sort by, sort by, sort by. I want to see these alphabetically. Maybe that will help. And instead of doing this tab, 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 tab thing, let's do a CSV. Yeah, let's do a CSV. That's not a comma separate, that's a semicolon separate. So it's a SCSV. But okay. Is there a fast grower in there? Could we just throw away part of the search space? Let's grab the example because that's a smaller. No, let's not grab the example. Maybe the... Yeah, the thing has to be in the example as well, right? If there is a thing, it has to be in the example. Yeah, because we get the solution for the example as well. The thing has to be in here. I'm gonna see if we can double our search space without it crashing. Oh, it's getting close to the burning point. What is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think this might be 20 runs. So that's our max. Longer than this and our CPU burns. But what's the pattern? Is there a pattern? Is there a pattern? We have what? We have 4 different characters in our example at least. Do those look related in any way? Don't see it. Let's take a look at the input again. Do we see, in this small example, do we see something we can use? It looks random to me. I don't see it. If you've solved part 2 and you know a pattern, a solution I don't need, a hint I could use. And otherwise, it will be something for tonight. Let's take a look here. This almost doubles, but it's not really doubling. What's the not really part? 18. Maybe let's print out the current generation as well. That's not what I was looking for. I'm looking for current generation, which is N. That's not really the place to do it. Let's do that before. Yeah, so now we print out the generation as well. Let's run this code again. Oh yeah, we are printing out. Let's do it the other way around. So repeat 0, and if it reaches 20 and we do a +1 instead of a -1, then we'll see what we want to see. Better. But did this help us? Not at all. Oh, come on. It's not even doubling. In the beginning, it's not even doubling. It's from 2 to 6. Mm-hmm. Nope. How can we proceed? When you're very stuck, take a shower, I always say. Am I going to follow my own advice? I think so. I completely lost steam, and doing the naive thing, we burn our CPU starting from 20, so we're only halfway. And looking at those numbers, I don't think dot length that returns like an int. I don't think we will be able to use that strategy anyway, because this looks longer than an integer. Let's see if that is actually true. Yeah, so we're outside of the range of allowable ints. So count by and this max by thing. Yeah, actually that will work. No, count by. Count by returns an integer probably. Yeah. So this will not even work, this strategy. We need to do something smarter. And the brain is saying that I'm not smart enough to solve this right now. So I am going to take a shower, and hopefully I will have the eureka moment so we can solve part 2 somewhere later tonight. So yeah, a bit of a bummer. I'm happy with part 1. Part 2, it's one of the usual gotchas. Every year of Advent of Code has these. They just require a bit more thinking, and I will not bore you with me staring at my screen for another hour. So thanks for watching, and I hope to see you later in the day for part 2. Bye-bye.